So, in case of Boolean expressions, so we can represent it in two different forms. One is known as sum of product form, another is called product of sum form. So, as the name suggests, sum of product means it is a summation of product terms. For example, this A B plus A C. So, A B is A and B. So, as we said that if it is obvious, so we do not write the dot in between to represent the and. So, A B is the first product term, A C is the second product term. So, overall expression is the summation of the terms A B and A C. So, that it is in sum of product form. Other alternative for this Boolean expression representation is product of sum, where we take the sum as individual components like A plus B or A plus C. So, these are individual components, and then we take the product of those components to come to the Boolean expression. Now, instead of simply being the variable, so it can be the complemented forms of that also, like this is also a correct form. So, A bar B plus B bar C. So, that is also some sort of expression where it is. So, this is also a sum of product form, but here this A bar B. So, these individual terms they are slightly they are a bit so individual terms. So, they are in some complemented form. So, that can happen. So, whatever it is, so based on that we can have different forms for the functions. Now, but the problem with these forms is that it is not unique. For example, for the same expression, so we can have different forms. Like I will take an example and try to explain. Like if I have the term say A B bar plus B bar C or say B C bar. So, this is one form. Now, if you expand this A B bar, so it can be written as say A say we can write it as say somebody may write it as A B bar plus B into C bar into A plus A bar. So, if you expand this, you get like A B bar plus A B C bar plus A bar B C bar, because this A plus A bar is equal to 1. So, we can always write in this form. So, what is happening is that you see this is also sum of product form, this is also sum of product form. So, the problem with these forms is that one of them may be some sort of minimum form, and some other one is not that minimized. So, it has got 3 terms in it, the first one has got 2 terms in it. So, it is not mandatory that this minimized form they will be unique. Okay. So, that is the problem with Boolean expressions. So, if the minimum term expression may not be unique, there may be multiple expressions with the similar type of cost in terms of number of product terms, number of variables. So, this A, B etcetera. So, these or the complement like A bar, B bar. So, they are called literals. They are called literals. So, this number of literals in these expressions may be. So, in this case in this expression we have got 4 literals, in this expression we have got 1, 2, 3, 4, 5, 6, 7, 8 literals. So, number of literals may vary. So, literal means the variable or its complemented form. Then we have got this term. So, this A B bar is a term, similarly A B C bar is a term. Okay. So, we have got literals, term, and then the expression, the whole expression. So, coming back to our discussion. So, we have got how to check like two expression whether they are same or not. So, for doing that there is a canonical representation. So, anything that is canonical means, so all expressions that are equivalent they will boil down to the same canonical form. Okay. So, that is the beauty of this canonical form of expression. So, this standard sum of product or product of sum, each term of Boolean expression must contain all the literals with or without bar that has been used in the Boolean expression. So, it says that when you are taking the sum of product or product of sum, so individual terms they should so all the literals should appear in the individual terms. If it is not, then it is not in the canonical form. So, if the condition is satisfied, then the Boolean expression is said to be in canonical form of Boolean expression. So, it is called canonical because now it becomes unique. So, for a particular Boolean expression, so you can have only one canonical form, canonical sum of product form, and another canonical product of sum form. So, you cannot have more than one canonical form for the same expression. So, if you are given two expression and to check whether they are equivalent or not, they are same or not. So, what you need to do is to convert them into their canonical forms and then check whether the terms are same in both the expressions. So, say AB plus AC. So, here in the first term the literal C is not there. Similarly, in the second term this B is missing here. So, it is A and C, these two literals are present. So, B is missing. So, this is why this AB plus AC is not a canonical sum of product expression. So, how to convert this AB plus AC non canonical form into a canonical sum of product form? So, this is simple by using the Boolean identities. So, what we do? We write this AB as AB dot 1, we write it as AB dot 1 plus A dot 1 dot C. Then what happens is this AB is so AB is there, this 1 can be rewritten as C plus C bar, and this can be written as B plus B bar into C. So, that is what is done here. So, we substitute this in place of 1 we write here C plus C bar, in place of 1 here we write B plus B bar. Then if you expand, so you will get this form ABC plus ABC bar plus ABC plus ABC bar. So, these are all equivalent. So, from here we are getting this, from this we are getting this. Now, you see that some of the terms are appearing more than once, the term ABC has appeared more than once. So, you can just remove the duplicate and write it as ABC plus ABC bar plus AB bar C. So, this is the canonical form. So, whatever be the different forms in which you write this, like somebody may write it as A into B plus C, okay. Somebody may write it as say A B C bar plus A B C plus A C. So, in this way different people can write the same first expression in different form, but if you convert it into canonical form, then all of them will become same. That is the beauty of the canonical form. So, another expression is, so this is this AB is AB plus AC. So, this is converting into canonical POS form. So, this is not SOP. So, this is POS. So, this is POS form, product of sum form, from which is also known as the standard product of sum form. Okay. So, we have got the POS form. So, how do you do it? So, AB plus AC. So, this can be written as, so A plus B plus 0 into A plus C plus 0. Now, these zeros can be rewritten as C bar here and B bar here. Then we apply the distributive law, where this is the first term, this is the second term. So, you remember the distributive law, A plus B C is can be written as A plus B into A plus C. So, this is if this whole thing is considered as A and this is considered as say B C, then it is A plus B. Okay. So, that is A plus B plus C in this case, and we can write it as x and y z better. So, this is say x and this is say y z. So, this is written as, so this part is my x, this is y. So, this part is my x. So, this is z. So, you can distribute the thing. Similarly, for the second term also, so we can distribute this B bar into the two constituents. So, that way finally then if you remove the duplicates, so you get, so this A plus B plus C is coming twice. So, you can remove them and you can get it once. So, this way we can convert the product of some expression into their canonical forms. Next, so how to convert from product of sum to sum of product, or sum of product to product of sum is like this. Product of sum to sum of product. So, this expression is very simple. So, you just go on multiplying the thing, like say I have got an expression like a plus b bar into a plus c into a plus d. So, what you do, you just multiply a plus b bar by a plus c. So, this gives us this term a plus a b bar plus a c plus b bar c, then that is equivalent to a plus b bar c. Why? Like say this one, sorry, like say this one. So, a plus a b bar. So, it can be written as a into 1 plus b bar, that is equal to a. So, the first part a plus a b bar can be converted into a. Now, this a plus a c, so it can again be converted into a into 1 plus c, that is equal to a. So, the first three terms of the expression here, so it boils down to a. So, ultimately we have got a plus b bar c, and then we can multiply it by a plus d. As a result, we get this expression a plus a b bar c plus a d plus b bar c d. Again you have to take common, and so a is a, then this a plus a b bar c. So, by a similar logic, a plus a b bar c is equal to a into 1 plus b bar c. So, this 1 will be, so that gives rise to a. So, so this part a plus a b bar c gives me a, and with that if you do a plus a d, so if you do a plus a d, then you will be getting again a common. So, 1 plus d. So, that way I will get a finally, again from here I will get an a. So, it is a plus b bar c d. So, that is the whole multiplication that we have done. So, some product of sum to sum of product conversion, we can do it like this. Similarly, sum of product to product of sum conversion, so you have to factor out. So, this is a plus b bar c d. So, it can be written as a plus b bar into a plus c d, and again if you factor out. So, a plus b bar is a plus, it remains as a plus b bar, but a plus c d can be rewritten as a plus c into a plus d. So, in this way we can convert from sum of product to product of sum, or from product of sum to sum of product from. Of course, they are not canonical in nature. So, to convert to canonical, so we have to again do it, you have to convert to canonical form, like say a plus b bar c d. If you want to convert, so you have to write it as a into b plus b bar into c plus c bar into d plus d bar plus a plus a bar for the second term, a plus a bar into b bar c d. Now, if you just go on multiplying this, so you will get the canonical sum of product form. And similarly, for the second expression, like say a plus b bar into a plus c into a plus d. So, you have to write it as like a plus b bar plus c c bar into a plus c plus b b bar plus a plus d plus b b bar. Then that is not the end, because after this, after you have factored out this, so you have got like say terms like a plus b bar plus c into a plus b bar plus c bar plus the other terms that I am not writing here. So, again this has to be factored out. So, this is this c. So, we have to write the first term as a plus b bar plus c plus d d bar. Again the same thing will be happen for the others, and then it will be rewritten as a plus b bar plus c plus d into a plus b bar plus c plus d bar, so etcetera etcetera. So, this way you can convert, first you convert from sum of product to product of sum, or product of sum to sum of product, and then if you want to convert to canonical form, so you have to expand like that. So, when you have converted an expression to this canonical forms, product of sum or sum of product, so we come across two new terminologies. One is called min term, another is called max term. So, individual term of this canonical sum of product expression, so they are also known as CSOP. This canonical sum of product we often write tell it as CSOP, canonical sum of product. Similarly, here we the canonical product of sum we write as CPOS. This is so CSOP form. So, it is so individual terms of this canonical SOP form. So, they are called mean terms. So, mean term is the product of all literals within the Boolean expression with or without the complementation. And in case of this product of sum expression, the canonical product of sum expression, the individual terms, so they will be called individual sum terms, so they will be called max terms. So, max term is a sum of all the literals with or without bar within the Boolean expression. So, in this way we define mean term and max term for Boolean expressions. So, this is the thing like say 0 0. So, this is the corresponding mean term is x bar y bar. So, 0 1 corresponding mean term is x 1 y, like that 1 0 and 1 1. So, x y bar and x y. As far as max term is concerned, so they are written as mj. So, this is written as x plus y. So, you note here that for while writing the max term, so for if the value of the variable is 0, we are taking it as uncomplemented form. So, that is the convention that we have to follow, and whenever the value of the variable is 1, so we are taking it in the complemented form. Whereas, for writing mean terms, when the variable is in true form, so we are writing it in true form, and when it is in complemented form like say 0 0, so we are writing it as x bar y bar. So, mean term, so all the mean terms mi should evaluate to 1 for each combination of x and y, and the max term is the complement of the mean term. So, this is the complement of this. So, basically x bar y bar, if you take a complement, so this x bar y bar, so if you take complement, then by De Morgan's law it becomes equal to x plus y. So, max term is the complement of mean term. So, next we will see some problem. So, find the mean term designation of x y bar z bar. So, we have to so it is binary equivalent is 1 0 0. So, decimal equivalent is 4. So, it is the M4. So, this is the standard notation that we are using. So, this is say if this value evaluates to 0, so we will write it as M0. So, if this value evaluates to 2, so 1 0, so that evaluates to 2, so we write it as M2. So, by giving this number or index, we can directly understand what is the corresponding mean term. So, that is why this indexing is done. Similarly, here the indexing is done. We know that whatever be the value, so it is say 1, so that is 0 1. So, x should be taken in true form and y should be taken in complemented form for the max term. For the mean term should be taken in this x should be taken in complemented form and y be taken in true form. So, this x y bar z is 1 0 0. So, decimal equivalent is 4, and so this is M4. So, why do we need to do this indexing? So, mean terms are max terms are designated with an index, and this index number corresponds to a binary pattern. So, if you are talking about a particular function, so one possibility is that you write down the sum of product or product of sum expression. Otherwise, you can just tell that what are the indices like for the mean terms or max terms. So, that way you can also tell what is the function. So, that is why this index number is associated. So, index number for mean term or max term expressed as a binary number, it is used to determine whether the variable is in true form or in complemented form. So, for mean terms, 1 means the variable is not complemented and 0 means the variable is complemented, and for max term, so 0 means the variable is not complemented and 1 means the variable is complemented. So, this is the convention that is followed for this mean term and max term. So, indexing actually helps us to tell the function, like you can simply say that my function f is the summation of the mean terms. So, 0, 5, 9 and 11. So, this immediately says that since I am going to, so it is a 4 variable function because I am going up to 11. So, I will need 4 bits to represent it, and out of that the mean term 0, 5, 9 and 11, for them the function value is 1, whereas for others the function value is 0. So, this way this is a very standard notation. Similarly, I can have the max term representation, which is written as this pi or product. So, 1 5 7. So, this means that for this product terms 1 5 and 7. So, this I have to take the sum of product form product of sum form to express the function. Talking about so sum of product form of a Boolean function represented by the truth table. So, this is a a truth table means I have already said. So, we have to tell what are the input assignments, and corresponding to that what is the function, the output column. So, what will be the value of the function for this one, like say this is a truth table for this function. So, 0 0 0 is 0, 0 0 1 is 1. So, like that. So, if you consider only these values or the where the function f evaluates to 1. Okay, so, this is for this is for this 0 0 1, 1 0 1 sorry 1 1 0 and 1 1 1. So, 0 0 1 the corresponding index is 1, 1 1 0 index is 6 and 1 1 1 index is 7. So, my overall function is m 1 plus m 6 plus m 7, okay, in the sum of product form. So, this is a very standard notation that I put a sigma and within bracket we give the terms, or you can write it explicitly. So, it is x bar y bar z plus x y z bar x y z bar plus x y z. So, this way also you can write it. So, this is the from truth table to mean term to sum of product expression. So, POS form for this one. So, if you want to write the POS form, then we have to concentrate on the zeros. So, this is basically where the function value is becoming 0, I have to take those functions. So, those terms. So, this is 0 1 0. So, this is 0 1 0. So, I have got so for 0 1 0 the value is 1. So, I have to the function f. So, the function f in this case is function f in this case is the product of some form of this one. So, this is 0 1 0, that is value is 2, then we have got 0 1 1, that is 3, then we have got 1 1 0, that is 6, 2 3 6. So, which essentially means that the function when I am writing it. So, for 0 I will write in true form. So, x plus y bar plus z into 3. So, the 3 is x plus y bar plus z bar into 6. So, this is x bar, y bar or z. So, this is the sum of product, this is the product of sum expression. So, this is represented by max term like this, and then we can represent it in pi form, and then we can write down this thing. So, similarly, the second problem that it says that we write down the sum of product of sum expression for this. So, you can understand what we can do this here. So, this is 1 is 0 0 1. So, I have to write like x plus y plus z bar into the 3. So, 3 is 0 1 1. So, x plus y bar plus z bar into 6, that is 1 1 0. So, x bar plus y bar plus z into 7. So, that is 1 1 1, x bar plus y bar plus z bar. Okay. So, see, apparently it seems that it will how will it give the functions for different forms. So, this is this can be obtained like say this product of sum. So, if you expand it, so you will get if you convert it into sum of product form, then you will get the original terms for where the values of the variable is 1. Okay. Next, we will see how to minimize this Boolean expression. So, canonical sum of product or canonical product of sum is the derivation or expansion of Boolean function. So, it essentially we have got less number of literals per term, and that we are expanding to have more number of literals, and that converts into canonical form. but apart from the application in which you need to establish equivalency between Boolean expressions. So, this is not much useful, because while realizing the functions, what we will look for is the minimum sized realization in terms of less number of gates or less number of connections, like that. So, canonical forms are usually not minimal. So, there may be cases where the canonical form itself is a minimal form, but it is in general that is not the case. So, minimization of these Boolean expressions, so it needed to it is required to simplify the Boolean expression and thus reduce the circuit complexity. So, that I can use less number of gates, logic gates, to produce the same output that can be obtained by taking the canonical expression. So, this minimization of Boolean function is by itself a very important topic, and we will see some techniques for that, but keeping in mind that this minimization process is not very simple. So, in our course, so we will be considering Boolean expression with less number of variables, only 4 variable, 5 variable, at most 6 variables, and we will see that there exist exact methods for getting the exact minimum form corresponding to those functions. However, as those methods that we will discuss, so they are not applicable for number of variables say more than 6. Okay. So, if you are looking for larger number of variables, then exact methods do exist, but the problem is that they take enormous amount of time. Even if you think of writing a computer program for those minimization process, it will take enormous amount of time. So, keeping that in mind, so it is now, so many a time what we do is we do some heuristic minimization and be satisfied with that. Anyway, so that is not the purview of this course. So, we will be restricting ourselves to Boolean expressions of less number of variables, so up to 6 variables, and we will see some technique by which we can do the exact minimization.